Hello everyone, my name is Maggie Tansky and today I will be walking you through my report for Lab 2, Motion of a Falling Object. In this experiment I will analyze a real-life example of a falling object. I will then use Newton's second law to construct two computational models of the motion, one that includes only the effect of gravity and another that includes the effect of both gravity and drag. We will then compare the data from these three models and plot them together to see which computational model most closely resembles the real-life example. For this experiment, I decided the system to be a ball of paper and the surroundings to be everything else in the universe. I designated the origin so that the ball's movement would be in the negative y direction. Within the clip settings, I set the video's frame rate to be 30 FPS so the delta t between each frame is 0.033 seconds. Now I'll run the program. And as you can see, Tracker has generated a position versus time graph at the top right with the individual time position values generated in the bottom left. Here I have used Excel to plot a position versus time graph using the values generated by Tracker. This is the graph we will compare the computational models to. For the first computational model, we set the initial position and the initial velocity to both equal 0, as the ball's initial position was defined as the origin and the ball was dropped from rest. J hat, which determines the direction of the y-axis, is vector 0, 1, 0, so that up is the direction of the positive y-axis. We have set the while loop to start at t0 and iterate every 0.033 seconds until t equals 0.667 seconds. Within the loop, we define the weight of the ball to be the mass of the ball, times g, times negative j hat, because the weight, or the force of gravity, points down. In this case, the weight of the ball is equal to F net. We then use Newton's second law to determine the new velocity of the next iteration and the new position of the next iteration. When we run the code, this is what we see. The position versus time graph that is generated is very similar to the one from Tracker, but let's see how they compare when plotted together in Excel. As you can see here, the two lines are very similar except for at the end, where the gravity-only graph dips below the observed graph. I think this is because there is another force acting on the ball besides gravity. This force is drag, or air resistance. Now, in order to create a computational model with both gravity and drag, I need to tweak the previous code a little. The initialization remains the same, but the while loop gets an addition. The equation for drag is the negative of the proportionality constant b times the velocity of the ball. We also add Fd to the net force. But how do we find b? I found it by changing its value until the final position of the computational model was equal to the final position of the observed motion. So for this ball of paper, b equals 0.0032 newtons times seconds per meter. When we run the code with these additions, this is what we see. Again, the position versus time graph that is generated is very similar to the previous two, but we will again turn to Excel to see them all together. The third line is initially similar to the other two, but diverges from the observed motion about halfway through. Here we see a velocity versus time graph of the two computational models. Because the line for the gravity-only model is nearly linear, this means that the acceleration, which this graph represents, is nearly constant and therefore approaching terminal velocity. The graph for the with drag model curves at the end, so it does not predict a terminal velocity. Now we look at another velocity versus time graph, this time including data from the gravity-only model with the negative non-zero initial velocity and the data from the gravity and drag model also with the negative non-zero initial velocity. As you can see in the graph, the blue line, gravity with VI, has the same slope as the gray line, which is gravity only, just displaced in the negative direction. Therefore, the terminal velocity achieved by the ball in the gravity plus initial velocity model would be more negative than the original gravity-only model.